Hello, today we're going to look at electrostatic forces. This should be a review for everyone from 1211, but just in case, I want to make sure everybody's on the same page. So electrostatic forces, we can also call this electrostatic potential energy. And we look at it in terms of Coulomb's law. So our electrostatic potential energy, we can determine it using Coulomb's law, or we can get an idea of it using Coulomb's law. So our electrostatic potential energy is the potential energy due to two charged particles being some distance apart from each other. And these, as I said, are given by Coulomb's law. And our Coulomb's law, we calculate it as a force. So it is a force is equal to K, our Coulomb constant, times by Q1, which is our first charged particle, and Q2, our second charged particle, all divided by r squared, our distance. So K is a constant, Q1 and Q2 are our charged particles, and then r is the distance. Okay, so we can think about this in two different ways. We can have Q1 and Q2 being same charge, or like charge. I guess I should put like charge. They can have a like charge, both positive, both negative, something like that. When that occurs, like charges are going to cause repulsion. That is going to increase our energy. We can also have Q1 and Q2 being opposite charges. And this is going to cause attraction. It's going to be an energetically favorable thing. So this is going to decrease energy. So when we take these two particles, we can think about them at an infinite distance apart or close together, getting them closer and closer together. When they're an infinite distance apart, we can consider that state kind of a zero energy state, and then we reference to that zero energy state. So let's look at what that will look like. So if you've got two like charges that are some great distance apart, far enough that they don't feel the repulsion between the two particles, that would be this energy state right here, where they are infinitely far apart from each other, so there is no repulsion, so we're basically at that potential energy being zero. As we decrease the distance, getting them closer and closer together, there's more and more repulsion, and that energy is going to go up. We can have the opposite idea occur, right? We can have two opposite charges. Those opposite charges, again, when we are an infinite distance apart and they don't feel the attraction between them, they're going to be at that energy equal to zero. And then as we get them closer and closer together, because that is an attraction, an energy favorable thing, our energy will go down or become negative relative to that 0 point. Okay, so our potential energy itself is going to be proportional to our charges, our magnitude of our charges, and the distance between those, right? The greater the magnitude, if we are talking about either positive, negative, or positive and negative, the potential energy, whether it is a positive or negative effect, will be greater, and then the smaller the distance, the greater that potential energy. Okay, so we are talking about charges. So what type of things are going to have charges? So what is going to look at electrostatic potential energy? And of course, within chemistry, we think, hopefully first, protons and electrons. So both protons and electrons have charges. Positive charges for our protons, negative charges for our electrons, right? Generally, if we have a molecule, those protons and those electrons are going to even out, and we won't have an overall charge. But when we have a case where our protons and electrons are not evened out, we get charges within our molecule. One can be a complete imbalance of protons and electrons, and that's when we get ions. So our ions are a difference in the amount of protons and electrons. And this will result in a very large Q value, right? So you'll get actual full charges with ions. So the Q term for our potential energy is going to be based upon the magnitude of that charge. Okay. We also, hopefully, remember another imbalance of protons and electrons when we have a polar molecule. Okay, with a polar molecule, we've got partial charges. So ions have full charges, but polar molecules have partial charges. And it is again because of an imbalance of those protons and electrons. Electrons, if we have a molecule where the electronegativity and the electrons are balanced out throughout the molecule, then we're not going to have any partial charges. But if electron density gets shifted in a molecule due to atoms with greater electronegativity, then we are going to get partial charges because those electrons are going to shift from one area to another, leading to partial negative charges where the electron density is shifted to, partial positive where they have shifted away from. Okay, so this is going to be caused by a shift in electron density. And that shift in electron density is, with a polar molecule, we get what's called a dipole within, or a molecular dipole within polar molecules. So we have an area of positive charge, area of negative charge, all in one molecule. Okay? We get this when we have polar bonds. So two atoms covalently bonded, that have an electronegativity difference. So delta En is my electronegativity difference. They have electronegativity difference of greater than 0.4. We get that from our Pauling scale. Hopefully everybody remembers. So if we have a polar molecule, it has to have polar bonds, right? So something like an HCl bond. That will result in a polar bond where the electron density goes away from the hydrogen towards the chlorine, so towards the atom with the greater electronegativity, giving us a partial negative charge and a partial positive charge. Okay. Another thing that we have to have within a polar molecule is asymmetry. Right? If we have dipoles and those dipoles are getting canceled out, then we don't have a polar molecule. So that asymmetry will allow us to have a polar molecule. So let's look at some of the ways that we can get asymmetry. So I'm going to bring up a program, this one right here. So Just going to look at this real quick. This is a fun program that we can play with to look at how electrostatic potential energy is affected by change in electronegativity. So if we have two atoms that are the same electronegativity, then there's going to be no difference in the electron density, right? The electron density is going to be more or less even throughout. Okay? As we take one of our atoms and it becomes more electronegative, we're going to shift that electron density towards a more electronegative atom, in this case B. It's a little bit easier to see it as an electrostatic potential energy because I have pretty colors. So the electron density is going to shift towards atom B, and that produces a bond dipole and partial charges. Because we only have two atoms in this case, all the density is going in one direction. Electron density is going one direction, so we can see a visible partial positive and a partial negative. When we get more complex atoms, like so, 3 atoms, and we change their electronegativities, we can see how this is going to be affected. Now this particular one, we have a electric field, so we have a negative plate and a positive plate. Negative will attract positive, positive will attract negative, so on and so forth. So, as we change electronegativity of an atom, we can change that dipole in a specific direction and cause a molecular dipole to be produced within here. This molecule has asymmetry about it because it is a bent shape. However, if we were to move this to get a linear molecule, one that has symmetry, we would no longer have a bond dipole. Or sorry, a molecular dipole. So you see that our molecular dipole, the orange, which we can produce by adding in a bent shape, will go away as we become linear, because now that A and C are the same electronegativity, our bond dipoles become, or they get canceled out. So let's just real quick look at a couple of, or look at all of our symmetric and asymmetric geometries. So if we have polar bonds and we have a symmetric geometry, the ones that are shown on the left, then we will cancel out our bond dipoles. And that's because they're going to be equal but opposite directions. If you have asymmetry due to different atoms around a central atom, then this will not hold true. But if all the atoms around the central atom are the same, all of our bond dipoles will cancel out, leaving us with no dipoles with the molecules on the left side. So this includes linear, trigonal planar, tetrahedral, trigonal bipyramidal, linear within trigonal bipyramidal, octahedral, and our square planar, which is a octahedral geometry. Okay, and then our asymmetric geometries include bent, a trigonal planar that has a bent molecular geometry, a trigonal pyramidal within a tetrahedral electron geometry, a bent molecular geometry within a tetrahedral molecular or electron geometry, seesaw molecular geometry within a trigonal bipyramidal molecular geometry or electron domain geometry, T-shaped within a trigonal bipyramidal electron geometry, and our square pyramidal within our octahedral electron geometry. And it's because we can get a dipole. Now this one is going to be nonpolar because we do not have polar bonds. It's just a asymmetric geometry. This one, we have a bond dipole that goes up like so. Here, this one also goes up. Here, we have a general direction like that. Here, we have a general direction like that. And here, general direction like that. So none of these are going to have their dipoles canceled out. Okay, and that is everything for this pre-lecture video. See you guys soon.